Okay, this will be chapter 33, the last lecture for Physics 102, so loud cheering all around. We're going to talk about radioactivity and the atomic nucleus a little bit more. I'll start off by talking about radioactivity in general, how it's actually not a bad thing, but it could be used for good things, although too much energy is probably a bad thing, so I'll talk about X-rays and stuff like that. I'll talk about the types of radioactive emission that we can have. I'll talk about alpha, beta, and gamma emission, naturally occurring sources. This is all kind of related to what holds the atom together, so I'll talk about the nuclear strong force. I'll talk about when radioactive emission is going to occur. I'll talk about something called the half-life, how we can detect these things, how we can artificially cause elements to transmute, and I'll finish off by talking about radiocarbon dating. So what is radioactivity? Well, what radioactivity essentially is going to be atoms that are excited and they're trying to shed some of that energy. And when we talk about radioactivity, very typically it's going to be high energy things. The atom that is excited could emit an alpha particle, and all an alpha particle really is going to be a positively charged helium nucleus, so 2 protons and 2 electrons. It could emit a beta particle, which is essentially just an electron, or it could emit some gamma radiation, which is essentially just going to be some high-frequency electromagnetic wave. Now, when it comes to radiation, first of all things in the electromagnetic spectrum are radiation. Light is radiation, and light is not a bad thing. So not all radiation is bad. However, if we were to look at the spectrum, we know we cover this huge range of frequencies. And as frequency goes up, we kind of move in this direction. We know, for example, as we work our way through from the infrared up through the red, through the violet to the ultraviolet, we know that frequency is going up. And we have our good friend, energy is equal to Planck's constant multiplied by frequency. It kind of makes sense that as the frequency goes up, so also must the energy. This is why ultraviolet light can burn us and infrared light cannot. Now, above ultraviolet, we're going to have things that are higher energy. We're going to have X-rays, and X-rays can penetrate soft tissue, but maybe not necessarily bone, or at least not very deeply. And above that, we're going to have this thing called gamma rays, and these can penetrate quite a bit further than X-rays, and higher frequency, higher energy, and they're also more likely to damage things like our DNA. Let's just take a quick little look at the early pioneers of radioactivity, and what I always seem to say when we talk about atomic physics or quantum physics, this is new stuff. This stuff is, 200 years old at best, and that's kind of humbling, and also it's important. So around 1900 or so, this fellow by the name of Röntgen discovered X-rays, and that's a picture of his hand wearing a little teeny tiny ring. A fellow by the name of Rutherford, I mentioned him earlier, he discovered alpha particles and beta particles. Again, alpha particle is just a positively charged helium nucleus. Becquerel, I forgot to mention him, he was a discoverer of radioactivity in 1896, and he discovered that elements could radiate. And we have the Curies, and they discovered many radioactive substances such as radium and polonium. Interesting aside, she is the only woman to get a Nobel Prize in physics and chemistry. Although I will note that many of these people, they didn't know that they were working with things that were kind of dangerous. So, for example, many of them, such as Madame Curie, she died a very early death. Her husband, Pierre, probably would have, but he got hit by a car. Now, the way that Röntgen discovered X-rays was he actually had a beam of electrons, and he had some gas inside of a tube. Now it's called an X-ray tube. And he put some high voltage across that and got some electrons flowing from the cathode to the anode. And what they did was they bumped into some of the gas that was inside the tube, and he found that something came spitting out of the tube, and it was not attracted to magnetic fields, so it didn't have a charge. It had to be a wave. It didn't really bend or refract in glass. It could ionize the air, and it had lots of energy because it could pass through solid materials like his hand. Now, what are X-rays? Well, they are high-frequency, high-energy electromagnetic waves, and they're usually caused by electrons that are hopping in the innermost orbit of atoms. Picture for just a second an atom in this gas, and it's going to have this ground state right down here. And maybe it's going to have a really, really, really big jump until the next excited state. And then maybe n is equal to 3 would be here, and then 4 would be here, and 5 would be here, and 6 would be here. We know they get closer together. And what he found was if we had a bunch of energetic electrons kind of coming in, they could excite electrons from the innermost orbit all the way up to this guy right here. That's a big jump, lots of energy difference, lots of frequency. So usually they're caused by electrons that are making this big jump from up there to right there, and so we're going to get our X-ray right here. Now, he called them X-rays because he hadn't really seen anything quite like that before, and they have high energy. They can go through many layers of soft tissue, muscle, fun stuff like that, and they are a very useful form of radiation because they can show images of the bones inside of your body. Bear in mind that X-rays are a useful form of radioactivity. They're useful and they're kind of dangerous, but not entirely dangerous. Some exposure isn't going to hurt you, but way too much exposure is probably not a good thing. That's why the nurse puts that lead-covered apron over you whenever they take X-rays, whenever you're, in there for a broken bone. Now, exactly what is radioactivity? Well, radioactivity is just going to be a form of nuclear decay or radioactive decay, and essentially it's going to be an atom that is trying to lose some energy. It's been going on forever. It's not new. It's naturally occurring. It's in the air we breathe. It's in the rocks, especially around here. And it's actually one of the things that causes Earth to maintain its temperature. It's a natural process. There's nothing to be afraid of when it comes to radioactivity. That's like being afraid of light. And I'll talk about how much radiation is good for us and how much is bad for us in just a little bit.